So I want to say this one more time for emphasis. In order for this notation to be meaningful, there has to be exactly one correct vector to write over here to make this line not nonsense, right? Otherwise it would be meaningless. So it was very important that when we set up this vector equation, and in turn we solved it as we turned it into an augmented matrix and reduced it, and we got a unique solution. It was very crucial that we got a unique solution. If we had had less than 3 pivot columns at this stage, that would mean that we'd have a parameter, or maybe more than one parameter. And in that case, there would be infinitely many choices for C1, C2, and C3, which means there's be infinitely many ways to make this vector equation work. And in turn, there would be infinitely many vectors that we could put here, in which case this would no longer be a well-defined symbol. So it's very crucial for this notation to make sense. It's crucial that we get a unique solution at this stage. But the good news is that is guaranteed by the fact that our set B was a basis for R3. Okay, so this fact coming up generalizes this now and says this in a more formal manner. Okay, so let's start with the most general situation. You've got a subspace H of Rn, and you've got a basis B for that subspace. Okay, so assume that that's the case. Now, if you take any vector x from your subspace H, and then you set up a vector equation that's going to look like this, and then you use linear algebra and you set up an augmented matrix, and you carefully row reduce it to solve that linear system to figure out what your coefficients C1, C2 up to Cp would have to be, you're only going to get one solution, always. That's a guarantee by the fact that B is a basis of the subspace H. Okay, so in that case, we give a name we give another name. We've used lots of names here. These are called the coefficients of the linear combination, or the weights of the linear combination. But they're, in this context, we say that they're the coordinates of the vector x, but relative to the basis b. So this is how we'll write it. Coordinates of x relative to b. And then if we put those coordinates together into a vector, then this is now called the coordinate vector of x. Again, relative to b. We have to be very clear now which basis we're referring to. So that's why this subscript, so the notation is over here, right? You put the vector x in square brackets and then write b as a subscript. By the way, some books will use round brackets, which is totally fine. But what really matters is that you have to specify the basis. Because let's just go back up to this example again. What if we changed these basis vectors? If we changed this and replaced it with a different basis, well, then that would change this vector equation. It would change the entries of this augmented matrix, and it would conceivably change the solution that we end up getting, which means it would change this vector. So this subscript here is an integral part of the notation. If you change the basis b, you may change, you're probably going to change the coordinates. So we do not drop this subscript b. Okay, let's look at another example. Okay, so we've got well, let's start. We got what? We got H is the span of V1 and V2. Okay, well, what are V1 and V2? They come after. So we're told what V1 and V2 are. They're both three-dimensional vectors. So right off the bat, you know that since H is the span of some vectors, you know that it's a subspace of R3. Okay, but the question might be, well, do V1 and V2 form a basis for H? Well, remember there's two requirements for a basis. First of all, they got to be linearly independent. And then second of all, they have to be a spanning set for H, which means that H has to be equal to the span of V1 and V2. But that's true by just the way H was introduced, right? So it's automatically a spanning set. So as long as those two vectors are linearly independent, and you can check that they are, just do it in the usual way. Set up a vanishing linear combination and show that the coefficients must be 0. And once you check that, then you'll know that they're linearly independent, which means that they are a basis for H. So that's what we have at this stage. Before we start this example, we've got a subspace H and we've got a basis B for that subspace. So we do kind of have this is looking like the setting of this fact. Okay, so which is what we need to have, the setting of this fact to be able to talk about coordinate vectors. Okay, so what are we asked to do? First of all, we're asked to show that this vector x is in H. Okay, so it's a three-dimensional vector with coordinates 3, 12, and 7, and we need to show that it's actually belongs to H. So let's start by doing the usual thing. We'll set up x, as a linear combination of our basis vectors v1 and v2. And then now it's up to us to figure out what c1 and c2 are. So, well, if we write out the same equation in terms of its coordinates, we're going to get 3, 12, 7 is equal to c1 times 3, 6, 2 plus c2 negative 1, 0, 1. Okay, so that's the vector equation that you're going to get, and that's going to give you, when you go to solve that, you're going to get the augmented matrix given as follows. And then when you go to row reduce it, what you'll end up getting is this. You'll get the following. And that's going to tell you, once you get to this stage, that's going to tell you that C1 and C2 are given by 2 and 3. Okay, so that tells you how to write x as a linear combination of v1 and v2, and in doing so, that means it must be in this. If you know how to do it, that means x is in the span of v1 and v2, which means it's in H. So let's summarize that. So we can say, therefore, x is equal to 2v1 plus 3v2, which is in the span of v1, v2, which is equal to H. Okay, so that's the way to fully justify that x is in H. Okay, so what about part B? Part B asks us to find the coordinate vector of x relative to the basis B. Well, the good news is we did all the work in part A. Okay, so in part B, what do we have here? We have that the coordinate vector of x relative to B. Remember what this notation means? Think about this notation as asking a question. You're asking the question, how would I build the vector x in terms of or build it as a linear combination of the basis vectors in the basis B? In other words, what coefficients would I have to choose? So if we've already figured out how to do this, we've already figured out how to write x as a linear combination of v1 and v2. The coefficients were 2 and 3. So great, that tells you how to build the coordinate vector. Just going to use 2 and 3. All right, so that's all we had to do for part B. Normally part B would be asked in isolation without having, like here we did part A separately, and then we were asked to find the coordinate vector of x relative to B. But normally the way you would be asked this question, I shouldn't say normally, I should say often, you might not be asked this at all, right? This might not appear here, and you're just directly, right off the bat, asked to find the coordinate vector of x relative to B. So, okay, well, then you'd have to go through this process first, regardless of the fact that it wasn't explicitly asked for. This is part of the steps that are required to find a coordinate vector relative to a basis. But since we already did the work in part A, part B was short. Okay, what's part C? Part C is going the other way. In this case, we're asked to find a specific vector, y, but the only thing we're told about y is that its coordinate vector relative to the basis B is 1, 3. So, okay, well, so we're working backwards, right? We're just doing the same thing but in reverse. So I'm going to actually go up here so I have more space. So I'm going to do part C up here. So we can just do this. Y is equal to, and we can just build it as a linear combination of our basis vectors because this coordinate vector relative to B tells us how to do it. Just take 1 and 3 to be your coefficients. So we'll just take 1 times V1 plus 3 times V2. So that's going to be what? Here's V1 plus 3 times V2. And then when we add those together, I'll multiply the 3 in first. So you have negative 3, 0, positive 3. Then once you add those together, you're going to get 0, 6, and 5. So we can say, therefore, that's our vector y. 0, 6, and 5. All right, so here's another thing to think about. Y And this, we're going to go back through the whole thing now. Y is a three-dimensional vector, right? X was also a three-dimensional vector. But notice their coordinate vectors relative to the basis B are just two-dimensional vectors, right? This is a 1, 3, that's a vector in R2. And then the coordinate vector of X relative to B, that was just the vector 2, 3, which is a vector in R2. So that's kind of interesting. They're three-dimensional vectors, but relative to the basis B, they could be written as two-dimensional vectors. And this picture, you may have already been taking a peek down here. This picture kind of illustrates what's going on here. This shaded plane in this picture, that's really the subspace H. And what they've done really in this diagram, they've done really nicely, is they've shown you how every point in that plane can be written as a linear combination of the vectors v1 and v2, and you can sort of interpret it. Like if you look at the way this is drawn, it's drawn in like a grid-like fashion. It's like you've got a horizontal axis here, right? And this is like your 1 times v1, 2 times v2, and so on. And this would be 3 times v2. You got think of this as your horizontal axis and a vertical axis, right? It's kind of like you're plotting things in the Cartesian plane. It's just that you've got one of the axes corresponds to the vector v1 down here, and then the other axis corresponds to the vector v2. And then you can see up here, if you say, okay, that's, let me just get another color pen here. So if I take v1, that's v1, but if I take 2v1, that'll take me here. And then I could say, okay, that's v2, but if I want to take, whoops, I erased too much. But if I want to take 2v2, that would take me here, or 3v2, that would take me here. And if I add those vectors together using the parallelogram law, I'll end up getting this vector, which is actually exactly x, right? So I can build the vector x as a linear combination of v1 and v2, and this diagram shows you how that's happening. But really, what I think the diagram does a good job of clarifying, and I'm going to erase these annotations because I don't think they make anything more clear once we're done that conversation. You can see that the space H really is a two-dimensional subspace, even though it lives inside of R3. So the vectors in H are three-dimensional vectors because they live in R3. But H itself is a two-dimensional subspace. So it kind of looks like just the Cartesian plane embedded into three-dimensional space.